Works out, thanks. So, hi, thanks for having us here. And we're very happy that we can give this talk here on multimodal and scalable VAEs. Recently, multimodal learning has become very popular in the machine learning community. Multimodal learning is about learning from more than a single data type, like for instance, images or text, but combining, for instance, images and text. Models like DALL-E or Imagen, which you might have heard of, achieved impressive results in conditional image generation. Conditional image generation is generating an image based on some input text. We have 4 examples here on the right-hand side. Probably the text is a bit too small, but let me, for instance, read the one on the bottom right, which says, "Panda, mad scientist mixing sparkling chemicals, art stations." And the outcome image is this fancy panda mixing some chemicals, fully kind of imagined by a neural network or by a machine learning model, which is, in my opinion, really impressive. These models are and were and are able to gain visibility far beyond the machine learning community. To that extent, they somehow form or define what multimodal learning is, or at least what multimodal learning and what a lot of people understand under multimodal learning. And despite their impressive results, they only focus on a special type of multimodal learning. They only do text-to-image generation, which is a unidirectional form of multimodal learning. And it is inherently bimodal. We, on the other hand, are interested in learning from multiple data types, which is resembled in the multimodal learning, and not just in the bimodal learning, which is represented by image and text. At least in my understanding, and I think also because of the computational costs, it's not clear how these huge models like DALL-E or Imagen would be extended to multiple data types, or at least to generalize this unidirectional way of learning into a joint learning scheme of multiple data types. So let us talk about how we understand multimodal learning and how it differs from these popular, very impressive models. Multimodal learning to us is like, how can we learn from multiple and different data types, here depicted as text, image, and sound with these icons, and how can we leverage the additional information coming from more than a single data type, and how can we understand the additional difficulties and constraints that arise when trying to combine them. I think the Morrissey wants to talk about human level understanding. And if you think of humans, we as humans have multiple sensory inputs, like we have vision, we can hear, we can feel and touch. So we inherently have kind of multiple input modalities combined, and that allow us to work and function and be alive. But additionally, we don't collapse if, for instance, we close our eyes and we temporarily miss an individual modality. We are interested in building models that kind of work in the same mode or modus operandi. We want our models to benefit from multiple data types, but we also want them to not suffer too much if data types are missing. Different to DALL-E and these models presented before, we would like our models to jointly learn from all available data types, like to learn a joint representation that allows us to infer and predict combining all data types. So we want the latent representation or the representation of these models to be meaningful. Additionally, we would like our models to be able to generate all, but especially the missing data types that can arise. So let's say we have text and sound given, then we would like to be able to generate an image that makes sense, similar to DALL-E. In the missing data type regime, we would have this directed way of generating data. I forgot one thing. Everybody who works in machine learning knows how tedious and expensive labeling data is, which is already true for a single data type. If you think of having to label multiple, let's say 10 data types, this is kind of infeasible or at least too expensive to handle. So we are interested in models that learn or that are able to train without the explicit need for labeled data. Due to these constraints and their theoretical properties and their stable training dynamics, we focus in our work on variational autoencoders. In variational autoencoders, we optimize an elbow. A short recap: in the unimodal case, I briefly explained to you again the evidence lower bound. In the evidence lower bound, in the latent variable model, which the variational autoencoder is a part of, we try to learn the data distribution P of X, because the posterior distribution P of Z given X is intractable to compute. We have to rely on an additional variational distribution Q of Z given X. This Q of Z given X is freely choosable. By introducing this Q here, we are able to approximate the true data distribution, and the better the Q is fitted to the true posterior, the better we are able to approximate the true data distribution. If you think this is too complicated or not interested, we can also make it a bit more simpler. A variational autoencoder optimizes the elbow, but a variational autoencoder can also be seen as an additionally regularized normal autoencoder. So in autoencoder, we have an encoder that encodes the data X to a latent representation Z, and then decodes this latent representation Z to reconstruct the original data sample X. Again, here noted as X hat. And in autoencoder, we want the X hat to be as similar as possible to the original data X. In the variational autoencoder, we have additional regularization in the latent space according to some predefined distribution. Mostly it's normal distribution. So we force our latent representation Z to be normally distributed. Like this, it allows us to sample from the latent space, either random sampling, meaning from the prior, or posterior sampling or conditional sampling based on the inferred posterior Q of Z given X. This is true for a single data type. If we extend this to multiple data types, it is really similar. We again have this elbow, but we do not try to learn the data distribution of a single data type X, small x, but the data distribution of a tuple capital X. And the tuple capital X consists of M modalities or data types. Also, and in parallel, the posterior approximation Q of Z given X is conditioned on the full tuple and not on a single data type. This means that we try to learn a joint latent representation. Similar as to the autoencoder, also the variational autoencoder can be extended to the multimodal setting, which means that we encode the full tuple in the joint latent representation Q of Z given capital X, which is also normally distributed, let's say, and then we decode this single joint representation into the full tuple again, capital X hat here. And again, we want all the different modalities to be as close to the input data type as possible. So far, this is not really the multimodal setting is not really different from the unimodal setting. We just have a capital X instead of a small x. So what's the difference? The interesting part comes from additional constraints or an additional wish list. First thing is we want our model to be scalable because it needs to be able to handle missing data. If we have M modalities, like a tuple of M modalities, and we agree that it might be possible that some data types are missing, we have 2 to the power of M different subsets of modalities. So we would need to, in the vanilla way of programming, we would need to program 2 to the power of m different encoder networks, which is clearly not feasible for any m bigger than 2 or 3. So we need to find a way to, we need to find a formulation such that our model scales in the number of modalities m. Let's say we would like it to be scalable linearly in the number of modalities m. Additionally, we would like our latent representation Z to be meaningful. We would like to be able to infer interesting properties or predict some interesting task, let's say, independent which subset is given, independent of whether the full input set is given or if only a single modality is given. The same model should be able to infer a meaningful latent representation. Additionally, we would like to have coherent generation. What do we mean by coherent? Coherent means that, let's say, the text modality is missing here, and we just are able to encode sound and image. We encode to the joint distribution, and then we decode, let's say we generate the missing modality text head. Then it should be similar in the shared information to the sound and the image. Let's make an example. Let's say we have a text describing a bird. We have a sound which records the sound of the bird. Sorry for that words. And we have an image which depicts the same bird. So if we encode the image and the recording of the sound's voice, and we decode again to the text, and the text should describe exactly the same bird and not just some random bird, right? Of course, makes sense. So if we encode a penguin, then we should decode a text that describes the penguin, black and white and whatever. And of course, the quality of generated samples should be as good as possible. So let's say we decode not only a single penguin, but let's say 10 penguins, then the text should every time describe a penguin, but as we can imagine, there might be different ways of describing a penguin. So there should be variability in the modality-specific attributes, but consistency or coherence in the shared attributes between modalities. If we think of a way to make these models scalable, we kind of agreed to work in the late fusion regime. Late fusion means that we first encode every modality individually with its own encoder. So we have encoder 1, encoder 2, encoder J until encoder M into a latent representation given a single data type X1 or X whatever. Then these experts or these unimodal experts are then aggregated into a joint distribution Q of Z given capital X. From this joint distribution, we then sample a single sample to decode all modalities again with their own decoder again. So this means that because every modality has its own encoder and decoder, we scale linearly in the number of models if our multimodal aggregation block here depicted kind of aggregates in a scalable way. This means we need a function that works independently on the number of inputs. What has been done so far? So there are 2 previous works around that work in this scalable multimodal VAE regime. So the first work presented in Europe 2018 used the MVAE, uses a product of experts. A product of experts creates a joint distribution by aggregating the unimodal distributions over a product depicted here, as the name suggests. And because most VAEs have a Gaussian distribution in the latent space, the product of experts can be calculated in closed form and is again a Gaussian distribution. This means, or not this means, but in fact, kind of this if we have two unimodal distributions instead of three, we can take the product. If we have three, we can take the product. And so we don't need additional parameters for that. And we have a joint distribution, which is a Gaussian distribution, which lets us sample easily and decode again all modalities from the joint space. The second previous work uses a mixture of experts and was presented 1 year later at NeurIPS. And the mixture of experts is kind of a weighted sum of individual distributions. Here, every mixture component is the unimodal posterior approximation Q of Z given xj. And the way the joint distribution is constructed or how sampling works is a bit different. A mixture of Gaussians is not a Gaussian distribution anymore, if probably you know, right? So if we encode three modalities, maybe let's go back. If we encode all three modalities and we want to decode all modalities, we draw a single expert from here. So we draw one of here, which means that we select one of the three individual experts, and from this unimodal encoding, we then decode all modalities. We will come back to that later, or in Imant's part, we'll come back to that later. Before we are able to compare these two methods, let me first introduce quickly the data set we use as a toy example to highlight the failure cases of these methods and our own as well. So we construct an artificial data set which is based on MNIST, the digit data set, which combines or which connects modalities over the digit information. So the digit information is the shared information between modalities. Additionally, every modality, which is every row here, so we have 5 modalities, has an individual background. The background is sampled from a huge image, so there is kind of a distribution of a background. And we have 5 different background images, such that every modality has not only shared information, but only modality-specific information. Some of you might not say, okay, these are all images. Is this really multimodal? Fair, but kind of, if we go back to the example of the birds with sound, text, and image, kind of in that example, the bird species was the shared information, and the modality-specific information was how to describe a bird in the specific modality. Here we kind of went a bit simpler, so we only have image modalities, but the modality-specific information is really different, and it's not clear how to construct from the background 1, the background 2. So this means that we got rid of a few additional constraints to highlight failure modes without having unwanted confounders. So how did we compare the results or the methods? Of course, according to our wish list presented before. In these plots, on the x-axis, for all 3 plots, we have the number of input modalities, and on the y-axis, we have the performance metric. Let's start with the linear classification accuracy. So to evaluate the latent representation, we train a classifier on the latent embeddings and try to recover the digit information. So we train a linear classifier on the embeddings of the training data and evaluate it on the latent embeddings of the test data. The better we are able to classify these embeddings according to the digit information, the more information is still present in the latent representation. In this plot, we evaluate how this performance varies depending on the number of input modalities. So if we input the full set of 5 modalities, or if we input only a single modality. If we input only a single modality, this dot, of course, is the mean performance over all modalities. So the blue line is the product of experts model, or MVAE, and the green line is the mixture of experts model, or the MM VAE. We see that the blue model benefits a lot from having additional modalities built into the joint distribution. So in the beginning, the performance is rather low, but with increasing number of modalities, the performance increases quite a bit. The mixture of modalities, mixture of experts model has a stable performance. So for a single modality, it outperforms the MVAE model, but it is not able to benefit from additional modalities. So it only is able to fulfill one of the two desired properties. It doesn't suffer much if only a single modality is given, but it is not able to benefit if additional modalities are given. Different, the POE model it benefits a lot from multiple modalities, but also suffers a lot from multiple modalities. Then in the middle, we have the evaluation of the coherence of generated samples. So if we have only a single modality given and we generate the other modalities, do these other generated modalities show the same digit as the input image or not? Again, we have on the x-axis the number of input modalities, and on the y-axis the classification accuracy of these generated samples. So we trained a classifier using a neural network on the original training data, like the true training data, to classify the digits. Then we feed generated samples to these classifiers and see what digit they predict. If the predicted image matches the predicted image of the input image, this is a true positive. If not, it's a false, it's wrong. So let's analyze it. Again, the green line is the MVAE model and the blue line is the MVAE model. We see that the MVAE model, again, has a really stable performance. So it doesn't suffer from having only a subset of modalities as input. But different to the linear representation, the performance is quite good. So it's always above 70%. So with 70% accuracy, the generated image shows the same digit as the input images. Different to POE model. It suffers again a lot from only having a subset of modalities as input, benefits again from having multiple modalities as input, but is never able to outperform the MVAE model. So this coherence seems to be a problem for the POE model. If you go to the right, we analyze the quality of generated samples. So how variable in the modality-specific information are the generated samples? For that, we analyze the log likelihood of the test set. And the image, or what we see, is again similar to the previous plot. So MVAE has a stable performance, which is stable across independent of the number of input modalities. And MVAE benefits a lot from having multiple input modalities. But similar to the linear representation, latent representation, the MVAE is able to outperform the MVAE model, meaning that POE model or MVAE model is able to generate better looking samples or is able to better learn the data distribution P of X than the MVAE model. So what can we learn from this? Can we formulate the model which is able to combine the best of both worlds? Create good looking samples, have a good latent representation, and is able to generate coherent samples. What we tried is that we tried to create a model which combines POE and MOE. So in the first step, we take subsets and take a POE for these subsets, and then around the POE of these subsets, we create a mixture model. So we have a mixture of product of experts. The idea is that the product of experts is efficient in aggregating information coming from multiple modalities, and the mixture of experts is good in preventing a model from suffer from missing modalities. So we kind of try to incorporate both with this formulation. On the theoretical side, we are able to show that the mixture of product of experts, or MOPO, is a generalized version of the MVAE and the MMVAE model. The MVAE only takes the full set as input and makes a product around it. So it's a mixture model with a single expert, and the MMVAE model only takes the unimodal subset as input. So it's a product over a single expert, which is the expert itself. If we analyze the results, we see that our model is able, here the red line, to have a better latent classification than the previous two methods. It's able to outperform the other two methods in the coherence of generated samples, and it's to a big amount better able to create better looking samples than the previous two methods. We also see that in the extreme cases, let's say for one modality, here and here, the specialized model MMVAE performs a bit better. As well, kind of for all input modalities given, the generated samples of the MVAE model are better than the one from our model. But quite okay so far. So, is there anything beyond toy data? There are real-world applications which are based on scalable multimodal VAEs, analyzing single-cell analysis, or other interesting applications. If you're interested, check out these kind of references. We applied the MOPO model to the MIMICS CXR dataset. MIMICS CXR is a dataset of X-ray images and medical reports. There are two views from X-ray images, so front view and side view, plus an additional medical report describing the medical findings. And we wanted to know, is our model able to perform well in such a difficult setting? And we have to say, unfortunately not. As an example, I show you kind of a qualitative result of if we input a side view of an X-ray plus a medical report, which is longer than shown here, and I show you the conditional generation of it. At first, it's really blurry, right? So, I mean, if you would like to see any medical disease based on this image, good luck. But I think on this, we could have worked. So there are now VAE models which are able to generate crystal clear images and really nice looking samples. So I guess we could have worked on that. But more importantly, if we look at the original data sample, we see that our model totally forgot to include this medical device here, which is a no-go for medical applications. And even worse, the medical device would have been visible here in the input image and probably also be written about in the medical report. So kind of we found a new failure case for our multimodal models. By trying to understand what goes wrong in our multimodal models, we uncovered more general limitations of multimodal scalable VAEs. And with this, I hand over to Imant.
Okay. Not at all. Okay. It's there. Should be on. How's it now? Well, yeah. Okay, how is it now? Better? Perfect. Sorry for that. Okay, so Thomas has introduced multimodal VAEs and scalable VAEs, and what I'd like to do next is to point out a few limitations that we've discovered and that we've tried to formalize in our recent works. So the main takeaway will be that there are fundamental limitations in a certain setting. In the setting when information cannot be predicted across modalities. And I think it's quite intuitive and quite obvious what this means. So back to the example that Thomas has given, if one modality is kind of masked out or covered, such as the visual modality, for instance, then we can't infer everything from just hearing, for instance, or from the other modalities. So there's some information that's missing. That's quite intuitive, I think. And what has been formalized in different works and theoretically grounded is that if this information is missing, then the objective that's being optimized is limited by an amount that cannot be overcome by optimizing that objective. But in this work, we'll focus, like for the sake of this presentation, we'll focus on the empirical results because they are more intuitive, I think. And let's come back to the example of the polyamorous data set, where we can point out these different sources of information that we have for the data set. So we have, as one source of information, we have the shared information, which is by design the digit label that's used to pair these samples from the different modalities. And then another source of information is the modality-specific information that we have. So there are kind of different sources of modality-specific variation. There's the background color, which is the most obvious one, but there's also more subtle sources of variation, such as the rotation, the position of the digit. So if we would observe just one sample of one modality, we couldn't infer the correct rotation of the digit in the other modality, and we could do the same with the positioning, which is kind of fixed, but that's something that we'll also change a little bit in the following slides. And yeah, so for the purpose of this presentation, I'll focus on the empirical problems that arise through the modality-specific information. The first one being that we observe a discrepancy in the generative quality, and the second one being that we observe a reduced linear separability for the learned representation. So to the first problem, the generative discrepancy, let's again look back to the polyamorous data set, for which the result that we show here is structured as follows. So on the x-axis, we have again the number of modalities. Let me try to shift this. Yeah, anyway, it's the number of modalities ranging from 2 to 5. And on the y-axis, we again have the performance metric, in this case, the FID, the Fréchet inception distance, which measures generative quality, and lower values denote a better generative quality here. And what we observe here is that as a function of the number of modalities, for certain models, the generative performance becomes worse. And this is one form in which this gap that I pointed out manifests in the empirical results. So the models for which the discrepancy seems to arise are mixture-based multimodal VAEs. So thinking back to the formulas Thomas has shown, these are the models that use the mixture of experts within the aggregating function. And one might say that, but for the MVAE, there's no problem. It's on par with our baseline, the unimodal VAE. But the thing is that it lacks in terms of the other performance metrics, as Thomas has already shown. So for instance, in terms of generative coherence, there's a lack of performance for the MVAE. So there seems to be this fundamental trade-off between different metrics. And by the way, we use the unimodal VAE as a baseline because that's what also motivated our investigations in this direction. We observed that the randomly generated samples from the multimodal VAEs look qualitatively worse than from a simple baseline, the unimodal VAE. And to kind of create these results, we also control for such things as the capacity of the networks, of course, since we train with different numbers of modalities. So the second problem I want to point out is the reduced linear separability of the learned representation. And herefore, let's look at a variation of the polyMNIST data set. So on the left, you see the vanilla polyMNIST. On the right, you see what we call translated polyMNIST. And it's a simple change. We just add another source of modality-specific variation in the positioning of the digit. So before we kind of fuse the MNIST digit with the background, we shrink the digit and place it at a random location within this patch, basically. And the curious thing we observe is that the learned representations are much harder to classify when models are trained on translated polyMNIST as opposed to the original polyMNIST data set. So in subplot A, you see the performance of linear classifiers trained on the learned representations of the polyMNIST data set, of models trained on the polyMNIST data set. And on the x-axis, we plot different beta values. The easiest way to think about this is that beta is the kind of the most important hyperparameter in VAEs and multimodal VAEs. And we can vary the beta for all of these models. And what it does is it weights the KL divergence term in the objective. So the KL divergence relative to the likelihood term. And the beta is not really so important for the plot, but it's important that this does not seem to influence model selection. So over the range of beta values, the models seem to perform more or less the same way, but there's this severe gap when we look at the translated polyMNIST example. Here, the linear classifiers seem to perform randomly. So 10% would be the random performance. And we also check that this is not, this is kind of an artifact of the linear classifiers because the information is contained in the latents, but really it is harder to extract with a linear classifier. So this slide we've already seen. I just wanted to recap that empirically we've just seen these two problems that seem to arise when some information, like the modality-specific information, cannot be predicted, and when it influences the shared information as well, as we've seen for the translated polyMNIST example. And we want to pose a question because the prediction of the samples across modalities relates to the conditional distribution of pxi given pxj for I not equal to j. And what seems to be lacking in these models is a good estimation of this conditional distribution. So the question is how to improve this. And I want to present one idea that did arise in various previous works, including some of our own work, which is the use of modality-specific subspaces, or to be explicit, modality-specific latent subspaces. The idea is fairly simple. So to facilitate the estimation of the conditional distribution or the conditional distributions, we want to include site information that is predictive of the modality-specific information in the target modality. So graphically, it looks like this. We assume that kind of the natural assumption that we started out with, that there's shared information and modality-specific information, and we incorporate this also in the inference model, which is the reverse of the graph we've sketched out here for the special case of two modalities. And what we do is we rewrite the elbow using one shared subspace, as we previously had already. But in addition, we use M modality-specific subspaces. So capital M stands for the number of total modalities that we have. In the given example, 2 modalities. So in various works, people have shown that this also gives us an elbow on the, again, the joint distribution that we want to approximate. And the elbow looks slightly more complicated, but really all there is another expectation. So by the way, let me point out ZS is what has been Z before. We just make it explicit now that ZS, the subscript S stands for shared here. So basically that's what has been there before, including the KL divergence term, but what's new is colored in red on this slide. So this additional second expectation term that we see here is new, where we also infer the modality-specific posteriors. So basically the modality-specific branches of the inference model. And then what's important is then this is used as side information for the reconstruction, so for the likelihood term that we see here, which is now conditioned not only in ZS, what has previously been Z, but also on Zj for the target modality. And the KL divergence terms are not so important right now. Basically, we add them as well in order to be able to sample a test time also from these distributions for the modality-specific subspaces. And then there's one thing I also want to point out, because on the next slide, I'll show that the results seem to be improved, but we also observed in our own experiments that there's no free lunch really for this, because to kind of improve the performance with the use of modality-specific subspaces, what is often required is still the regularization of these subspaces, because if we wouldn't regularize them, then all of the information could go through the modality-specific subspaces, and the shared subspace could be kind of circumvented. And to regularize this, we need an explicit, to prevent this, sorry, we need an explicit regularization of the modality-specific subspaces. So in terms of results, here's one example, again, on polyanalyst, and this time we're looking at unconditionally generated samples, so randomly generated samples where the latent codes are sampled from the prior. And we do this for one modality here. So on the left, you see basically the vanilla MMVAE with the single joint latent space. And you see that the quality of the samples is slightly poor because they are average looking. So there's some diversity missing compared to the original data. And this seems to be improved by the addition of the modality-specific subspaces, which you of course tune. So this, again, this pointer that there's maybe no free lunch here. We had to tune the modality-specific subspaces by regularization. And what comes out is better looking generative samples and no trade-off in terms of the other metrics. So this is based on a recent work, which you'll currently find on arXiv. But I think it should provide the intuition already. Okay, so we've discussed the limitations briefly. We've introduced an idea of how some of these limitations might be circumvented. And now let's go over to the conclusion. But before we come to the summary slide, there's one rough comparison we would like to make, at least to provide some intuition. So please don't understand this slide as being technically correct as a comparison, but really it's for the purpose of providing some intuition and also fostering some discussion maybe. And what we're doing here is we're comparing this class of models we've presented, multimodal and scalable VAEs, with what we term here as state-of-the-art multimodal generative models based on the example of DALI, for which we've seen some samples in the beginning of this presentation. So for multimodal VAEs, we have the benefit that they are scalable with respect to the number of modalities. And models like DALI are currently limited to 2 modalities, for instance. Then multimodal VAEs try to solve a more general problem in trying to approximate a joint distribution, whereas models like DALI approximate the conditional distribution, and often only in one direction, such as image to text only. And then a benefit of VAEs, of latent variable models in general, is that the assumptions are stated very explicitly, and typically the implementation is rather straightforward. And on the side of DALI here, we are dealing with a very complex model that even consists of multiple separate parts. And there's complexities in multiple dimensions in terms of the data, like there's a lot of pre-processing and curation of the data required, a lot of engineering flows into the design and the tuning of the models, and last but not least, it requires a lot of compute. But of course, like the samples you've seen for multimodal VAEs are nothing like the samples we've seen for models like DALL-E, and that's where there's a huge potential benefit of looking at these models. So we see very impressive results for concrete tasks such as text-to-image generation or image-to-text generation, or maybe there's even models doing it in a bidirectional way right now, but still it's important that the question of whether we learn a joint distribution or whether we just do the conditional mapping in both directions. But this is exactly where the puzzle piece might fit in with the world of VAEs, because this is exactly where we observe the problems in terms of limitations for the estimation of the conditional distribution. So maybe some of the ideas from kind of the world of state-of-the-art, other state-of-the-art multimodal generative models might be interesting for multimodal VAEs as well. So really the takeaway from this slide is we think there's opportunities for cross-pollination across both of these fields. From multimodal VAEs to models like DALL-E, there could be interesting components that could be used, such as the different aggregation functions to make them more scalable, the idea to learn a joint distribution, for instance. And vice versa, obviously, for the condition generation, I think there's a lot we can learn from other state-of-the-art models. All right, and that already brings us to the summary slide. Briefly going through the individual points here. We've introduced multimodal VAEs as a class of models. The goal is to approximate a joint distribution. We've presented different criteria for measuring the performance, such as looking at the learned representations, measuring the coherence of the generation across modalities, and measuring the generative quality, obviously. And for an additional criterion, which is scalability, Thomas has talked about different aggregation functions that can be used to make multimodal VAEs scale with respect to the number of modalities. Then we've discussed limitations which currently affect most multimodal VAEs, especially for the approximation of the conditional distributions. And finally, we try to make a relation to other state-of-the-art multimodal generative models based on the example of DALL-E here. Okay, I will briefly go through the references here, but I won't read them out, of course, just for the recording. And then let me say thank you for your attention.
Okay, are there any questions?
I have a question. Thank you. So guys, thank you very much for the presentation. So first question is that, have you tried another type of data, such as like sparse data, where you have a lot of 0 ones or count data to test your approach and implement the comparison?
So what kind of real world data are you thinking about when?
Biological data, single cell data.
It often comes in counts.
Yeah.
Well, what comes to mind is that a different data type often requires a different likelihood distribution. Like maybe the Gaussian assumption is really incorrect then if we have that type of data, and some sort of categorical distribution might be more suitable to it. And definitely we'd have to redesign encoders and decoders, but I would argue that that's the case for every approach. So these are the two components that come to mind, kind of redesign of the encoder decoder and the likelihood objective that's suitable for this data type.
So another question, have you tested the sample size, like reducing the sample size in order to break the approach to see how much data you really need to learn something meaningful?
Yeah, that's a good question. So I am aware of previous works that do reduce the sample size, also the number of pairings between samples, because we kind of assume we always have this tuple of shared modalities. And there is work from Oxford that explores this, where there's also samples where the pairing is not given. So kind of, one could call it a semi-weakly supervised setting, for instance.
Okay, thank you very much.
Thank you.
Yeah, also thanks for the talk. One question, so when I think about this, when you have different modalities, you will be interested in how important is modality one in order to satisfy the classification task or something. So could you somehow compute a number or something? So modality one is 60%, modality two is 30%, and the combination is 10% or something? Or, I mean, that must also all be hidden in these conditional distributions, I guess. Or how do we approach this?
Yeah, it's a tricky question because we're not solving a task directly, really. We're doing reconstruction as a task. And for reconstruction, all of the information should kind of pass through the latent space. But still, even for the task of reconstruction, it could be interesting to measure how much each modality contributes to certain parts, especially if you talk about things like coherence, for instance. Would be interesting, but I didn't have that on my radar yet. Thanks for pointing out.
So thanks for your talk. I have two questions. First, regarding this polyamnest, could you maybe elaborate a bit more on what are the modalities there? Because I think you said it has 5 modalities, right? But to me, it was images, right? So I didn't understand.
Do you want to take this one?
Can you hear me? Yeah, okay. So we first started out with image, text, and sound, right? Where we also have different data types, right? Then we went a bit more abstract in saying a modality is defined by some shared information, which is shared with the tuple of modalities, and some modality-specific information. So we kind of got rid of the assumption that modality and data type is a different thing, right? So in polyamnest, we have the shared information as digit and the modality-specific information as the background. So, but they are all kind of, if you say, image modalities. So you're kind of, it's a bit more abstract to see this as multimodal, but kind of multimodal in a sense that every modality consists of modality-specific and shared information.
Thank you. And the other question that I have is regarding the optimization trick. I assume when we have these different modalities, then the latent is not a Gaussian anymore. It's a mixture, right? So then what would be like, I mean, intuitively, what would be the trick for the optimization?
So you mean the joint latent distribution?
Exactly. But I mean, for the reconstruction, I assume, like, you know, the initial trick will make it again like a unimodal Gaussian, right?
So you mean the output modality,
exactly,
the output likelihood. So also already in the unimodal VAE, the assumption is that the output is conditionally independent given the latent. So in the VAE, you also calculate the loss of the reconstruction with respect to the input on the individual pixel level, right? Mm-hmm. So for multimodal, we kind of extend this by saying the P of xj given z is independent of P of xy given z. So we kind of also have an individual pixel level loss, if you want to say so.
So if I understood correctly, then it's a sum of KL divergences for different modalities.
No, You mean this loss or the KL term? Just to be sure if I understand you correctly.
This one, yes, this one.
Yeah, exactly. So
Okay, I see that.
you kind of impose a distribution on the data type and you calculate the likelihood of your output under the distribution of your data type. And you do this on the data type level.
Okay, perfect. Thank you. Thank you very much.
Thank you.
Are there any more questions? Yeah, sure. People online, if you also have questions, maybe you could already speak. No.
If I may,
Sure.
wait a moment, sorry. Yeah, I have to, because of bandwidth. I would be interested in to know what type of computing systems you know to do those calculations. I'm a big fan of computation that can be done on a home PC, but I don't think that this would be possible on a well, regular PC. Thank you.
I'm not sure I understood the question. So it's the question, what compute resources are required to train these models?
Yes, do you use TPUs, tensor processing units, high performance computing, or do you use regular PCs? Or what kind of computing systems do you use to implement your algorithms?
Perfect. Yeah, that's perfectly clear. So we are using GPUs for this. And we are computing on a cluster, but I would say that the models we've presented here could be computed on, a general purpose GPU, as some people even have at home. Training time is quite expensive, so for some models you need to train for a day or something, but it's nothing outstanding, like nothing compared to DALL-E and such models, of course.
So you don't need really tensor processing units on a large scale. So you could really do that on like regular NVIDIA RTX.
Yeah, so GPUs or TPUs would both work, I think.
Cool. Oh, thank you. Thank you.
Thanks a lot.
Any more questions from audience online? Okay, if not, then please join me in thanking again our speakers. Thank you very much. So, yeah, so I think the plan right now is to have a break for lunch, and I think we will be back at 1